In this lecture, we're going to develop a new tool for deciding when a series converges or diverges. That's called the integral test. Now, this is a nice tool to have in our toolbox since it's going to let us leverage everything we already know about integration to help answer questions about the properties of series. So the theorem starts off with a few requirements, right? We have to have a positive, continuous, decreasing function that matches the value of our sequences. That's this a sub n equals f of n part. Now, if we have all of these pieces in place, then we know one of two things. Either the integral and the series both converge, or they both diverge. So to prove this, we're going to leverage the ideas that you learned in first semester calculus about Riemann sums. Right, so suppose our f of x function looks like this graph here, right? It's continuous and it's decreasing, and we're going to assume it matches up with the individual terms of our series. So what I'm going to do is I'm going to take the x-axis and I'm going to look at the section from 1 to n. So I'm kind of thinking in terms of the nth partial sum here. And I'm going to take that and I'm going to divide it evenly into segments that are 1 unit long. Right? So once I've done that, I'm going to draw these rectangles going up to the lower side of the curve. Okay. Because I divided this evenly into unit lengths, the endpoints here are 1, 2, 3, 4, ... up to n. So the heights of these rectangles are all the values of the sequence, the a sub n. And because their width is 1, the area of each of these rectangles is equal to just the individual sequence values. Okay, so let's write that here. Right, the sum of the function values from 2 to n, right, because we're doing the right-hand edges of the rectangles, is equal to f of 2 plus f of 3 plus so on out to f of n. So that's the lower Riemann sum. Let's think about the upper Riemann sum. Right, if I replace this with the upper values, now we've got the same thing going on. Right, the left hand, the height of each of the rectangles is a sub 1, then a sub 2, then a sub 3, all the way over to a sub n minus 1. Right, well again, those are just the function values. So the upper sum is the sum from 1 to n minus 1 of the function values. Okay, so because the function is decreasing, when I found that lower sum based on the the right hand endpoints, those rectangles were all below the curve, right? So that upper sum there underestimates the area, right? So it's going to be less than the integral. Similarly, the second sum here, based on the upper rectangles, that is going to overestimate the area. So that sum is going to be greater than the integral. Okay, so let's write that. Right? The sum from 2 to n is less than or equal to the integral, is less than or equal to the sum from 1 to n minus 1. Excellent. That right-hand sum, that's just the n minus first partial sum. That's s sub n minus 1. The left-hand one, that's a little trickier to think about. It's almost the nth partial sum, but it's missing the first term. It's missing a sub 1. Now remember, a sub 1 is the same as f of 1. So here's what I'm going to do. I'm going to replace the left-hand sum with the nth partial sum minus that missing value, minus f of 1. And I'll replace the right-hand sum with s sub n minus 1. Okay, so let's hold on to that. Right, I've just written that up here at the top so we have it for reference. Now I want to consider these two cases. Right? What if the integral converges? Well, if the integral converges, then it equals some number. Right? Let's call that number L. Okay, so I want you to look at the left-hand part of the inequality. Right? This piece here. I'm going to replace the integral on the right-hand side with L. Right? So if I do that, it becomes this, s sub n minus f of 1 is less than or equal to L. Now let's add, remember we're always going to be talking about the partial sums here, right? The sequence of partial sums. So let's add f of 1 to both sides. This is what I needed to see. First, this tells me that the sequence of partial sums is bounded. L plus f of 1, that's a number, right? So there's an upper bound on the sequence of partial sums. I also know that the sequence of partial sums is monotonic, it's increasing. Remember, because our function is strictly positive, right? Because it's strictly positive, the values of the sequence are strictly positive, which means to get the nth partial sum, I add some positive number to the previous partial sum, right? So because the sequence of partial sums is monotonic and bounded, right? We saw a previous theorem a few lectures back. That means that this sequence is convergent, right? And if the sequence of partial sums converges, that's our definition for saying that the series converges. Okay, so that's the first half. Second half, what if the integral diverges? Well, the integral diverges, that means that the limit, I'm using kind of the language we use for when we're talking about improper integrals. The limit as n goes to infinity of the integral from 1 to n of f of x is equal to infinity. Okay, now let's focus on the right-hand side of the inequality. Right, that's telling me that the nth, that the sequence of partial sums is greater than the integral. Well, but the integral is infinity. Right, so that means that the sequence of partial sums also must be going off to infinity, which means that sequence is diverging. And again, that's our definition for the original series diverging. So that's what we needed to show. Right, that shows if the integral converges, so does the sequence, the series, and if the integral diverges, so does the series. Okay, so I got a couple links here. One of them goes to the next lecture where we're just going to continue adding to our techniques for proving convergence versus divergence of series. And the other one goes to another example video where I'm going to talk about something called a p-series. And we'll see how that relates to something else called a harmonic series, which you've kind of hinted at a little bit in some previous lectures. And we'll use this integral test to talk about when that series, when those special series converge or when they don't. So, and of course, if you like this lecture, please don't forget to click on the like button down below as well.